Okay, so thank you very much, Giuseppe, for the introduction. I did a bit of changing the title just to simplify a bit and remove lots of words, just keeping managing containers and Kubernetes in EGI. It's a great pleasure to be the first webinar presenter in this season. We already kind of covered this topic in the previous series of webinars, but now I want to have more content on some of the technologies we're using in EGI, and we have better understanding of how they work. Just to set a bit the expectation, this will not go very deep into anything. It's more like an overview of what we can do and what you can do mostly with containers in EGI. There are lots of details that are not present in the slides, and I will not go over them in the presentation, but of course we have the time for the questions, and we have the possibility to talk in other occasions to with more detail into these topics. So I just get started. This is the outline of the presentation. So first I will start with what is a container, what do we mean here with containers, and why we should use them, and then a bit on the orchestration. So containers are nice things to run application, but when it gets complex, you need something else. So orchestration is something that normally comes when you start using containers in a big scale, let's say. Then from that introductory part, I will move into the more practical side of the things, explain a bit how to run simple applications with containers in EGI, different methods, we will see them. And then a bit on how to run Kubernetes in the EGI Cloud, and then a summary trying to cover or explain more or less what was described before. So get into it. Containers. So containers, I'm pretty sure most of the people know about them, but I think it's worth to still keep a bit of an introduction of what we mean here by a container. So container is mostly a virtualization at the operating system level, and this is achieved by using the namespaces and cgroups features of the Linux kernel. So the namespaces, what they give you is isolation, meaning, for example, if I start a process in a given namespace, it will not be able to see other processes, or it will not be able to see all the different network interface that is available in the host. So these namespaces provide isolation. And then we have the cgroups that provide control, meaning limits on resource usage. For example, I can say this container, so the process and whatever it has with it, can only use 1% of the CPU, or 2 gigabytes of RAM, whatever kind of limits you want to put. Normally, there is this kind of image used for comparing containers and let's say more traditional virtual machines. And there you can see a bit the different overheads when going through one kind of virtualization or the other. Looking at the left, we have the VM-based approach. So we have the hardware where the things actually run. On top of the hardware, we have the hypervisor and the host operating system. These somehow are separated. Sometimes are kind of the same thing. So that's why I put it like a bigger box than on the right. And this is what allows you to create virtual machines. Then we have, in this case, 3 virtual machines. Each of them have an independent copy of an operating system. And on top of that, you have the applications with the libraries, the binaries, and whatever you want to have. So that would be kind of the VM-based kind of virtualization. And if we look into the containers, here we don't have the hypervisor. Everything is managed at the host operating system level. We have a thin layer, which is the container runtime, which is what creates those namespaces and cgroups and make them exist, basically. And then on top, we have the applications, which has the binaries and libraries and so on. But here, the kernel of the different applications will be the same for all. So they are sharing the host operating system, but they are virtualized at that level. Containers. Oh, sorry, I didn't want to do that. I don't know how I manage. Sorry, I hope you can still see the slides. Can you confirm?
No, we lost your focus. Yeah.
Sorry, and can you see it now?
Okay, now yes.
Okay, good. So I guess I need to click here. Okay, I was clicking on the wrong place of the screen and it was wrong. So alongside, let's say, the runtime, which is what I showed in the previous slide, there is the container images. Basically, that's a file, an immutable file with metadata and a set of file system layer that are the files that really will be run inside of this container. And this is normally built as layers, and each of the layers is a change from the previous image. So this is a very simple kind of stupid example. So you can start from a Ubuntu 20 image. On top of that, you run a command, which is installing Vim. And then that's a new layer that you have on the container. And what you get when you run it at the end is kind of the view of all the layers together. You will look at the top of this. You will see all the layers with the changes on top of each other. So container images are what you need to really run a container. It's the files that you will run when running a container. Container images can be made available in Container Registry, which are basically an online service for storing and retrieving images. Those images are tagged, and here you can see this is an example of a command line to get a specific image. So this is pulling the image in this registry, which is called EGI Cloud. It's just a name. The image is cloud info. That's kind of the container we want to run. And the tag is, you can have different versions of this thing. So in this case, it's latest. Docker Hub is kind of the main and most popular of this registry, and it's there at the web. It's basically free for anyone to push your containers and to use, although it has some limitations. I mean, if you do a very heavy usage, then it may not suit your needs, and also has things like if you're not paying, your images after a given certain of time will be removed. So something to consider if you're looking for a very long time preservation of images. Probably this is not the right place, or you need to go for a paid plan, just to consider. So said that, why would we want to use containers? So there are kind of three things that make containers a nice thing. First, with containers, you ship all your application code and dependency in a single package. So this container image basically contains everything that you need. And it's very easy to move from one place to another. So you can run the same thing everywhere from your local laptop where you're developing to the production machine, and it will be the same. That also brings a bit of reproducibility, because if you can run the same thing with the same software everywhere, then probably you're able to reproduce the same execution. Although, of course, there are details here that may not make that possible, but in principle, you get good reproducibility with containers. And it's quite easy to share using those registries. You saw before, just doing this Docker pull, you just get an image. You can build on top of that. You can push your new image into the registry, and then you have a very wide ecosystem of images available everywhere, and it's very easy to move from there. Then the second point is the container share the machine operating system kernel. That means that there is very little overhead. when running a container. So it's almost like running in bare metal on top of the operating system. So this is really nice if you are looking for performance, or if you're looking for consolidating servers and just having more of these containers in a single piece of hardware. And the other thing is containers are also isolated from other applications. So it's nice to run things that are different, but somehow you can run them together in the same machine, but still don't see each other. Of course, as they are sharing the same kernel, security is, I mean, is let's say less secure than a virtual machine approach, but still it's quite some boxes, and normally what you see in a container is not available in the other. There are some more things to consider into the container world. There are two things called the container engines and the runtimes. Here I put some definition I took from Red Hat. So the engine is the software that accepts the user requests, including the command line, options, pull images. So kind of wraps all the steps needed to make the container run. And you have things like Docker, CRI-O, Podman, Singularity, Udocker, etc. The main or the most known out there is basically Docker. And then the container runtime is kind of the lower level component that it's inside the engine, and it's the thing that will actually run the container. There is kind of a standard reference implementation called runc. This was coming from Docker that was split into several projects, and one of them was runc. Then, well, now it's contributed by several people. And most of the system actually rely on it. So at the end, you kind of have the same runtime everywhere, at least for, let's say, more commercially oriented engines. For the ones more looking into, let's say, HPC, HTC kind of computing, like Singularity or Udocker, then you probably have other kind of runtimes also available. So that was mainly to introduce Docker, which is, as I said before, the main or mainstream container engine out there. It was the one that created like the trend for containers in the computing world. It's a complete ecosystem around containers, so it just allows you to manage everything related to containers. It just one command line that allows you to deploy things very easily. It's providing tool for building the containers, for pushing the containers, for pulling it, and lots of people are using it. So it's quite easy to find what you need in the Docker ecosystem. As I said before, Docker was kind of a monolithic thing, but then it was split into the Docker engine, containerd, and runc. So now we have like Docker engine is the more command line interface, the more user-oriented thing. Containerd is a daemon that manages everything, and runc is what actually executes the containers. One thing that needs to be taken into account with Docker is that it basically requires root access. So it's assuming you have control over the machine you are running Docker in, and that makes it not so suitable for some systems like HPC or HTC systems. Just some screenshots of what you can do with Docker. This is a very simple example of just Docker run. This is interactive and emulating a console. So this IT, and I'm running the Python 3.9 image. So this is an image that is in the Docker Hub, and when I type that Docker run IT Python 3.9, basically Docker will go to the Docker Hub, will find the image, and will bring it to the local computer, will extract it, and will run it. And since this is Python 3.9, basically what it's running is Python, and I just did a hello world. So this is a very simple example of running an application with Docker. Normally what you do is that you create containers. And for that, you have what is called a Docker file, which is a set of steps that you want to execute on top of the base image to get your own container. So again, very simple example just to let you understand how this works. So I created a very simple Python code that is just a print. I have this Docker file, which is starting from the Python 3.9 image. I copy this file into the image, and I say, this is the command I want you to execute. So very simple, as I said, it's just adding a file to an existing image and saying this is the executable I want to run. So I can do just Docker build, and I'm naming this Enol /test. This will just go through the Docker file and run the different steps. And then I can just run it. So Docker run, the same name, and it will run whatever I put here in the CMD, which is this hello py, which is this simple print. So this is very simplistic example. You can have way more complex things. This is a real example of one container we're using for the operation of some components on the EGI Cloud. Again, this is a Python application, so starting from Python 3, but here we have some installation of Python libraries. We are changing the default shell. We are running some commands. In this case, this is getting the IGTF CAs and install them into the machine. It's copying some other files and so on. There are lots of different kind of commands that you can add in the Docker file. So here you have some examples, but there are multiple more. And there's lots of documentation and lots of examples in the Docker pages. So I would suggest to just check that or ask if you have any questions. So this is basically how you create your container and you run it. So you build and then you do Docker run and you have it. But what happens if you need to go beyond a single container? So imagine you want to run a microservice application, and you have lots of different pieces there, different containers for each of the microservices running. You need some cooperation between them and so on. So it starts to get complex, and you probably need something to make it easier. There are several possibilities here. The first one is just use Docker Compose. Docker Compose is a tool from the Docker ecosystem that allows you to define an application that is composed of several containers that are somehow related with them between each other. So you have a file where you specify which are the containers you want to run, how you want to communicate within them, and how to interact with the storage, so the volumes that you will use in this application. And basically you have a very similar command line interface, which is the Docker Compose, very similar to the Docker command line interface. So you have Docker run, and then you have Docker Compose run. It's very kind of the same, just changing the file that you want to, the file with the specification of what you want to run, and that's it. And if one machine is not enough, because Docker Compose mostly just stay within a machine, you probably need to go for container orchestration. So before getting to the container orchestration, just one example of Docker Compose file. Again, this is very simplistic, and just an example taken from the Docker pages. This is saying, well, services, the different containers I want to run. I have two here. So one is called web, another is called Redis. The web one will be built from a Docker file that is available in the current directory, and it will expose the port 5000 to the outside world. It will see this same directory as /code, and this other as var log, and it will be linked with the Redis, meaning that when I start this web container, I will have some environment variables telling me that Redis container, you can find it at this IP with this port. So you can basically in your application just read this environment variable and connect to that. The case of the second container is Redis. It's just running the image named Redis, which is available in Docker Hub. And this is a volume, well, this is a volume that is basically empty that is available here. So that's kind of what you can do with Docker Compose. Of course, this can grow a lot. You can have lots of different services and relate them with different kind of links, but this is the main idea. So going for container orchestration, you have multiple applications, each of them composed by single containers. You want to run their infrastructure. You need something that makes that happen. So a container orchestrator will do that for you. What it will do, it will take the containers, put it in the hosts that you have available for running, will take care that they are always running and restart them if needed, provide the network between the different containers so they can communicate. It can scale up and scale down the number of containers that you're using, depending on some policies that you can define. And it will also allow you to discover where my different pieces of the applications are located. There are several technologies here. I would say right now, Kubernetes is kind of the de facto standard and what's taking the lead here. Docker Swarm is something that comes from Docker, but it's not being used so much. And Mesos is a system that has a long history and is able to do some container orchestration. But lately, Kubernetes is kind of the thing that everyone is using. So on Kubernetes, just a few words. Kubernetes is quite a complex platform, but it's quite nice once you really understand and get used to use it. Kubernetes is an open source platform for doing this kind of orchestration of containers, so automating the deployment, scaling, and operations of application containers across cluster of hosts. And it basically does all the things that I said before, putting the containers on whatever they need to be put, restart them whenever they need it, provide basic monitoring, logging, health checking, and enabling containers to find each other. So this is an open source coming from Google initially. Now it's hosted by the Cloud Native Computing Foundation. And although it's mostly targeting more this kind of enterprise microservices kind of application, it's more and more used in the research world, also for running more research-oriented applications. So I think it's really interesting to also be aware of this and being able to support that in EGI. Which brings me precisely to that, how we are supporting containers in EGI. So first slide here, I want to introduce something that it's in beta, but I think it's worth to mention. We are all working on in a container catalog also in the EGI side. So this will be a place where people could share the containers and would be easy to find containers. Focus, of course, on research. This is just a screenshot with a very preliminary preview, but it's kind of a heads up. This is coming. We will work on having an EGI container registry and front end with this application database. So similarly to what we have for the cloud VMs and for generic applications, we will have a similar container catalog in the DAppDB. So said that, let's go to the details on how you can run containers on EGI. So the first option is, okay, EGI provides you a cloud service where you can run whatever you want. So just do that. You can use the EGI Cloud Compute to spin up a VM and install Docker and run containers there. So basically you get to choose what is the operating system that you want to use. You get to choose what's the container engine or runtime or whatever combination you want to use. And of course, you also get to choose what's the VM size. So you can run on a very small one, on a very large one. So that's always there. You can do it, but probably that's not what you always want. Mainly because installing Docker and so on is kind of someone can do it for you, and we do it. So basically what you can do is rely on the EGI Docker VM image. And this virtual machine image that we can maintain from the EGI Federation. And it's just installing Docker, Docker Compose, kubeadmin, which is a tool for installing Kubernetes. So you have it already there. It's updated every 6 months. So we take care of making sure that things get renewed. And if we discover any vulnerability or get notified of any vulnerability, we also update this image to make sure that we have the latest and more secure version. It's based on Ubuntu, which I hope suits most of the people, but we can talk about supporting other operating system if that's needed. And with that, you still have the possibility of choosing the virtual machine size, so you can run large or small applications, but at least you don't need to worry about installing, let's say, the basic machinery. So this is available on most of the providers on the VOs of the EGI Cloud. So you can just select this image and run it. But maybe you don't want to manage a VM. I understand not everyone wants to become an administrator. That comes with some responsibility. You need to take care that the VM is up and running, that there are no issues with it, there are no security vulnerabilities, and so on. So it can be a burden. So there are other services in the EGI portfolio that can help you to run applications with containers without caring about so much the underlying infrastructure. And that's the EGI high throughput compute in the world of Pioneer. The problem here is that Docker requires root, and this basically won't be allowed. So we need an alternative way of running these applications on this kind of systems. So we need an HTTP-oriented container engine. And of course, this is not meant to run services like an HTTP server and have like limited lifetime or resources. This is more like job-like execution of applications. So it's something that we take an input, do some processing, and produce an output. So here we have two engines that we support in the EGI infrastructure. The first one is Singularity. This is a project that came from the US. It started in 2015. It started at LMBL, but now it has a commercial company behind, which is called C-Labs. And it's quite focused on the support of HCC and HPC. So it's containers for these systems. So it doesn't require any root access for running a container. It's trying to do or to make it easy to use the system features like GPUs, InfiniBand, file systems, so you can run MPI applications, you can run applications using the GPU, and so on. So it's trying to make it easy for you to exploit the HPC features of the system. It mostly relies on the system that is around to set the limits, so it's not so much using these namespaces and C groups, although it has also a bit of use of that. It mostly relies on something else to set those limits. For example, if you submit a job with a batch system, that will be already setting the limits. It maintains the user credentials, so wherever the user you are in the host, you will be the same user in the container, independently if the container says that it wants to be root, you will be always the same user as in the host. It has a peculiarity with the image format. It doesn't follow this kind of layer approach that Docker images have. It has a different format, but still it's able to import the Docker or Open Container Initiative images, which makes it very, very easy to use with the existing software that it's around. So just to give you an idea of how Singularity can be used. So this is just some examples of me running Singularity on a virtual machine. So I'm a simple user, and I'm trying to execute an image for Alpine. This is coming from Docker. So this is taking an image from the Docker Hub, downloading it, converting it to the Singularity format, and then running it. and I'm running this cat etc alpine release, which is this 3.13.5. You can also build images with Singularity. This is very simple example of building an image just by taking a Docker, an image from Docker and just building a Singularity without adding anything, but you can add stuff from in the build process. So I took the Ubuntu 20 image and I built a local one called myimage.cif, and then I can just run it. This is quite nice because basically this file, you can move it around. You can put it in CVMFS, for example, and you can have containers from there and use them easily. What else do we have for Singularity? One other thing that Singularity tries to do is try to make it easy to access what you already have in the host, particularly your home directory. So this is again a very simple example of this is my current directory. I have 2 files, and I just run on inside of Singularity a command for creating this file, and if I do an ls, it will be shown again. So alternative to Singularity, there is Udocker, which is a project coming from the wide EGI community. This was started in 2016 as part of the Indigo Data Cloud project, and now is part of the was included in EOS Hub, is part of EOS Synergy and Indigo Deep project. So there are lots of projects working with Udocker, and it has kind of a similar interest. Like Singularity tries to run Docker containers in an environment where you can normally not be able to use Docker. So it runs applications encapsulated in Docker containers without using Docker, without recurring privileges, without system administrator intervention, or without additional system software. Other things of Udocker, it's basically you can execute it as a normal user. You don't need to install anything. In contrast with Singularity, Singularity requires that the system administrator installs Singularity and configures it for you. Otherwise, it will not work. It has different kinds of execution models, and it's like a regular user process. It will just show up as any other process. So any other kind of controls or accounting will apply. And you can use it in interactive or batch systems. So Udocker has an approach shown a bit here. So basically, you can bring images from registry or from files, and you can bring them to your local repository. So you can do it with the pull, import, or load commands. You can what they call create an image that converts these layers into operating system 3. And then once you have that, you can basically run. And for running, you can have different backends depending on the capabilities of the host. So you can use this ptrace and sharelib, which will run almost anywhere, although it has some limitations. And then you have others that will rely more on the kernel features like the runc or Singularity if it's available as in the host. So similar to the Singularity examples, I have a bit of the same with Udocker. Here I'm showing how to install. So again, I'm a simple user. I'm just getting Udocker from GitHub, making it executable, just executing Udocker install, and now I have it. I can run the same command I was running with Singularity. So Docker run Alpine, cutting the Alpine release. So it will download the layers, and it will just start the container and have the result here. You can also pull an image and create this operating system tree, so you can run it later. So here I pulled the Ubuntu image I created with this name, and I reuse this name to just run this command, and it's there. And of course, it's also capable of seeing your let's say host file system. So you have this example where I touch a file in my home, and I'm doing that with my with this option bind home that will make the home in the container will be the same as the home in the host. So that was Singularity and Udocker. You can use them in the EGI high throughput computing. Singularity requires that it's already there installed. Udocker, you can just do this curl command and install it in your home, and both of them will allow you to execute containers within this environment without any further issues. So last option is, let's go for Kubernetes. This is mostly for bigger applications or more microservices oriented applications. As I said in the beginning, Kubernetes is not a simple piece of software. So it has a lot of moving pieces and things that need to cooperate between each other. And one important thing is how you make Kubernetes be available for you. And that's what we try to do with the Cloud Container Compute service, which is still in beta, but it's quite available for use right now. So this service gives you the ability to deploy and scale Docker containons on demand using Kubernetes. So it relies on EC3, the Elastic Cloud Computing Cluster system, to automate the process of this deployment. EC3 has a graphical user interface, but also a command line interface access. It's fully integrated with check-in, so you can use your typical credentials. It will discover the cloud provider features, so it will discover which cloud providers are available, which are the images that are available, and which are the sizes, and so on. And this builds on EC3, of course, but also on Ansible and kubeadmin, which is a tool for creating Kubernetes clusters. I have here 2 screenshots of the graphical user interface that EC3 provides for doing this Kubernetes deployment. This is an example of the almost last screen before just going into the last step, where you have the summary of what was created. So basically, I selected here a site called TP3 in France. I selected Ubuntu 18 as the basic image. These are the kind of instances I will use. This was just one CPU, 4 GB of RAM. I will deploy Kubernetes, and basically I will start with one node and have this name. And once this is done, it will have this screenshot saying, well, this is your cluster, this is the IP where you can connect, you can download an SSH key to do so, and this will be your username. You have a video here that's coming from a demo that the EC3 people did in the last EGI conference. So I invite you to check that link with more detailed explanation. We also have access via the command line interface. Basically, this is a matter of configuring a set of templates with the configuration of the site that you want to use. And to make that easier, we have the Fed Cloud command line interface tool that allows you to create those templates. This well, again, very simple sample. This is showing the projects I'm allowed to use in the Seska site. And I'm using this 3A, which is the access one. And basically, I'm telling here the Fed Cloud tool to create these EC3 files for me, and it will create this auth. That will be the authorization file with my access token and the templates that are needed to deploy to Kubernetes. So that's just kind of a helper, and you have more information in this link. This under the hood, as I said, is mostly EC3. Basically, what you have here is that you create, or EC3 creates a Tosca description of what needs to be deployed. That's sent to the IAM infrastructure manager that will contact the cloud side, and inside the cloud side will start some VMs where this clues component will take care of checking what's the load of the cluster in any given moment, and it will create new worker nodes for your Kubernetes cluster as needed. And well, it deploy Kubernetes, it will deploy a dashboard, this tool, these kube apps for making it easy to install applications from Helm. And it will also install an ingress controller so you can access the cluster from the outside world without having to expose everything to the outside world. There are some EGI specifics. If you are into Kubernetes, this may be useful. The first thing is the service type called load balancer will not be available, mostly because load balancer relies on external features from the cloud provider. And here what we are doing is creating an ingress with Nginx that offers mostly the similar functionality, and it's quite easy to expand with auto configuration and let's encrypt certificates so you can get certificates easily for your servers. The volumes, we are using mostly NFS, so we can set up NFS on this very same Kubernetes cluster, and the volumes will be created from there. But we also support other technologies like Cinder, which is the OpenStack volume. We can talk about that if you need it, and we can also integrate with check-in. So if you want to do so, you can use check-in tokens for authentication authorization in the Kubernetes API. So you can access this API with your access token. So I'm getting basically at the end of the presentation with kind of the summary slide of how you can run containers in EGI. Basically, you have like three kind of application groups. So if you are looking into running jobs, probably you are interested in using high throughput computing, and you have Singularity and Udocker there. Singularity requires the system to be installed previously, so it's something that each provider needs to configure. Udocker, you can just basically bring it with you and run things. If you are looking into running things into a virtual machine, basically you can either bring your own image or use an EGI Docker image and log into that and use Docker as you would do in your laptop. And if you're looking into complex application, you can, of course, do your own Kubernetes deployment, but we offer this Kubernetes with Elastic Kubernetes as a service, which is this EC3, to make it easy for you. I have some docs reference here, links to documentation of the different things I have mentioned here today. Probably I'm missing something, but just ask if you are interested in learning more. And that's basically me. Thank you.